quick summary of interpretation. The average slope is change in the y quantity divided by the change in the x quantity, and that's the average rate of change of the y quantity with respect to the x quantity. And we illustrate this on a representative graph of representative trapezoidal approximation graph between some point where x equals a and x equals b, numbering the points that indicate our subdivisions by x naught, which is equal to a, x1, etc. Breaking the graph here, this graph might be miles long. It might run from here to Pluto, might run from here to the nearest galaxy or the farthest galaxy. We don't know how far this graph runs, but if we started here, ended here, and break it somewhere in the middle, we can sketch representative trapezoids, and in the middle where we break it, we include the ith subinterval. We don't know what I is, but this is going to be the ith subinterval. The ith subinterval runs from x sub I minus 1 to x sub I, just as the first interval runs from x naught to x1, second interval from x1 to x2. The interval ends at the x value whose subscript corresponds to the number of the interval. So the ith subinterval ends at x sub I. And of course we have here the ith trapezoid. The slope of the ith trapezoid is going to be the change in y, which in this case would be negative. It's going to be the rise. If we go from here to here, the rise is negative. It's about this big, divided by the run, which is of course equal to the width of the ith subinterval. So there's our average slope. Now, another aspect of the graph. If the y quantity is the rate of change of some quantity that we call q, q for quantity, with respect to x, so the y quantity, this quantity here, represents the rate of change of q with respect to x, then it turns out that the area is going to be the approximate change in q on the corresponding subinterval. So that on the ith subinterval, the two values of y will be two values of the average rate of change of q with respect to x, so that when we calculate the area by taking the average of those two y quantities, we're going to get the average rate of change of q with respect to x. Multiplying that by the change in x on the interval, we get the change in q. So that's the meaning of this statement, and in that case the area has a significant interpretation as the change in the quantity q, whatever that quantity happens to be. Okay, now you can see that I've written in a contrasting color the reasoning behind this statement. Average altitude then represents the average rate of change of q with respect to x, so that average altitude times width is equal to the change in q. Now the reason for that, second line, is that the average altitude times the width is the average rate of change of q with respect to x times the change in x, and that is the change in the quantity q. And you might want to review the whole definition of an average rate of change in order to completely understand that statement, but it should be clear from the context of many of our examples. And then for trapezoidal approximation graph on an interval from a to b, like the one represented here, the accumulated area through the ith subinterval is the change in the quantity q, and we're still assuming that y is the rate of change of q with respect to x. So the accumulated area through the ith subinterval is the change in the quantity q from x equals a through the end of the ith subinterval. Now, from x equals a, that's from here. The ith subinterval is here. The end of the ith subinterval is here at the point x sub I. So the change in q from here to here is going to be equal to the accumulated area, since the change in q for every subinterval is the approximate value of since the area of every subinterval is the approximate change in q on that subinterval, then when we add them all up, we get the total change in Q. And if we're going from x equals a to the end of the ith subinterval, that'll correspond to all these areas. So the accumulated area through the end of the ith subinterval is the total area in the shaded regions, including all the trapezoids between here and here, between x3 and xi minus 2, whatever I minus b, whatever I might be. We're going to include all those trapezoids all the way from here to here. It's going to give us the total change in our quantity Q. Again, assuming that the y quantity is the rate of change of Q with respect to x. And if you've had calculus, there's a connection in all this to the calculus. And if you haven't had calculus, well, it won't hurt you to see what these connections are, because someday you probably will. And you might want to make note of this. Calculus connections. First of all, the slopes are the average values of the derivatives, which represent average values of the rate of change of y with respect to x. You should understand that statement completely if you understand calculus. And if you don't understand the calculus, you probably would profit from going back to the calculus and understanding how this is the entire foundation for most of the first semester of calculus, where you're studying derivatives. Then the accumulated area is approximately equal to the actual area under the curve, and that represents the integral of y with respect to x on the interval from a less than or equal to x less than or equal to x sub I. Talking, of course, about this interval here, the interval that we've shaded. You have some actual curve, and the total of all these shaded regions, the total area of all these shaded regions is going to be an approximate value of the integral over the interval from a to x sub I. And two final comments about the connection with calculus. Whatever the interpretation of the slope is, and we've talked about how we interpret slope by interpreting rise, run, and then what it means to divide, that is the interpretation of the derivative. That is what the derivative tells us. Whatever that interpretation is the interpretation of the derivative. And the interpretation of area is the same as the interpretation of the integral.